So this is lecture 21, and we continue our study of eigenvalues and eigenvectors of a matrix. Actually, this leads to an extremely useful decomposition of matrices. So there is this theorem that if you have a matrix A, first of all, let's say what kind of matrix we are talking about. So for a large class of matrices, you can diagonalize them. Diagonalization of a matrix. This is our main topic for today. What do I mean by that? So not all matrices can be diagonalized, but a large class of them can be. So a diagonalizable matrix A, which is an n by n matrix, it only works for square matrices, is such that there exists an invertible matrix X, so that X inverse A X is equal to a diagonal matrix. So that means you are given this matrix, it would be diagonalizable. You will say that it's diagonalizable if there exists some other matrix X, which is invertible, so that you conjugate. This is called conjugation. From one side you multiply with an X inverse, and with the other side, on the other side you multiply by X, and as a result, the resultant matrix you get is a diagonal matrix. That means it has entries only on the diagonal and everything else is zero. So this is an extremely useful idea. First of all, so before we prove it, let's see how it can be used. So from this equation, if I multiply by X from the left, I get this. And then I multiply by X inverse from the right, I get this. That means my diagonalizable matrix, if my matrix is diagonalizable, then it can be written like this. You say that A can be decomposed into a product of X inverse, and X with a diagonal matrix. So this is the kind of decomposition you have over here. In the middle, you have a diagonal matrix, and from left and right you are multiplying by a matrix and its inverse. So one consequence of this is the following. I can, for example, do this. If I compute the determinant, if A is diagonalizable, then determinant of A is determinant of x d x inverse. I know that the determinants break down, and as we saw last time, determinant of x inverse is equal to 1 over determinant of x. So I get x 1 over determinant of x times determinant of d, and they cancel. So I'm left with determinant of d. But what is d is a diagonal matrix. So what is the determinant of this diagonal matrix? The determinant is just the product of the entries on the diagonal. And so you can compute the determinant in a very easy way if you know how to decompose this matrix into this form. And we will very shortly see that what is this decomposition. How does it look like? Similarly, if I compute the trace, so because of this decomposition, the trace would be x dx inverse. But I know that the trace is cyclic, as we proved in one homework. So this x inverse comes over here. So they cancel. So trace of A is equal to trace of D. So trace of A is again just sum of diagonal entries of D. Now I want to know what are these diagonal entries of D. Well, it turns out, as I'm going to prove, that this D is just the diagonal entries are lambda I are just the eigenvalues of A. So you started with the matrix A and it had some eigenvalues. N eigenvalues. So when you will decompose it into its diagonal decomposition like this, it's also, doesn't matter you write it this way, you can also write it this way, where you have just put x equal to y inverse, or x inverse is equal to y. So you can write it either way. Write x inverse on right hand side or write it on the left hand side. It doesn't matter. There's just some one matrix. There's just some matrix which you have to multiply from the left, and inverse of it you have to multiply from the right. So this, in this decomposition, this matrix is just composed of diagonal entries of consisting of the eigenvalues of A. By the way, so if you have a diagonal matrix, any diagonal matrix, let's say B is diagonal, let's say B looks like this, B11, B22, B33, BNN, and all others are 0. If I find the eigenvalues of such a diagonal matrix, what do I get? I have to do this. B minus lambda I determinant equal to 0. But B minus lambda I, this matrix will look like minus lambda, and everything else is a 0. So when I compute the determinant of a diagonal matrix is just the product of the entries on the diagonal. So I'll get things like this. I'm putting equal to 0. So I get B11 minus lambda, B22 minus lambda, and so on until I get Bnn minus lambda is equal to 0. That means eigenvalues are B11, this is the first one, the second one is B22, third one is B33, the roots of this polynomial. Until Bnn. So that means eigenvalues of a diagonal matrix are just the diagonal entries. So this means that in this diagonal decomposition, whatever I just argued before, that I have just claimed that these eigenvalues appear over here. So these lambda I are eigenvalues of A as well as D. So during this diagonalization, in this decomposition, whatever D you get as the diagonal matrix in this decomposition, it retains the same eigenvalues. The eigenvalues are not same. Similarly, the determinant is not changed, because when I make the determinant, as I just saw, these guys cancel. These cancel. So determinant is same. Similarly, I just proved that the trace is same of A and D. So many these kind of properties are retained when you decompose it into a diagonal decomposition. And from the diagonal decomposition, you can read off those things much more easily. Now, also, if this is true, which I haven't proved yet, that the eigenvalues of A are actually the diagonal entries of D, then from here, I find the determinant of A. This implies the determinant of A is the product of eigenvalues of A, because determinant of A is equal to determinant of D, and determinant of D, since it's a diagonal matrix, so it's just the product of the entries of the diagonal, but I'm claiming that on the diagonal of the D, it's just the eigenvalues of A. So determinant of A is just the product of eigenvalues of A. Similarly, trace of A is just the sum of eigenvalues of A. So let's see how can we prove it, this result. So first let me prove this theorem. If you have a bunch of eigenvalues which are distinct, so I have an n by n matrix, distinct eigenvalues of an n by n matrix A. So that means this k is either equal to n or less than n. I can consider all the eigenvalues or a few of them. And if they are distinct, this is very important. We know that not always the eigenvalues are distinct, but if they happen to be distinct, then the corresponding eigenvectors x1, x2, xk are linearly independent. So first of all, let me just explain what it's saying. So it's saying that I have these equations. Xk, and I know that none of these are equal to each other. None of them are equal. Then they're linearly independent. That means zero has only one solution, that is all Ci are zero. So how do you prove it? Proof. So if I consider the span of all of these, it will be some subspace, because spans are always subspaces. Some subspace of Rn, because these are n-dimensional vectors. And essentially, I want to know that what is the dimension of this subspace. So some of them, so what is the dimension of this subspace? Now suppose that all of them are linearly independent. And R is less than K. So I'm assuming that not all of them are linearly independent. I have to prove that all of them are linearly independent, but I'm not sure if they are. So I assume that only R of them. Suppose only R of them are linearly independent, where R is less than K. Well, some R will exist because if I consider only one of it, that one vector is always linearly independent, because you can never make one vector equal to 0 unless you put, unless C1 is 0. So this R could be 1. So at least one, if I pick one of them, that's always going to be linearly independent. But maybe there are two. So whatever the minimum number of these vectors is, which is linearly independent, I'm saying that number is R. So since they're linearly independent, then I will have C1 x1 plus C2 x2 up to CR xr equal to 0. But if I consider some other constants, 0 implies all Ci's are 0. Now I add one more vector from the set, of the eigenvectors. This must have a solution, where not all di are 0. Because my assumption is that R is the maximal set of linearly independent eigenvectors. When I add one more from the original set to this, they become linearly dependent. Since x1, x2, xr, one more added to it, are linearly dependent. But in this equation, dr plus 1 cannot be 0. Because if dr plus 1 is 0, then my equation reduces to the previous equation. And the rest of them, because rest of them are linearly independent, then the rest of the d's must also be 0. So dr plus 1 cannot be 0. So that means this vector is not 0. This implies that these d1 up to dr cannot all be 0, because they must combine to give me a vector equal to, so that it cancels with this one to give you 0. So not all of them could be 0, because if of all of them I choose to be 0, this part would be 0. So not all of them are 0. So then I take this equation, call it 1, and I multiply it by the matrix A. By matrix A. So I get these D1s come out. This is 0. But these are eigenvectors with distinct eigenvalues. So I get this equation. When the A acts on them, it reproduces them back with these eigenvalues. Now I call it 2 multiply 1 by lambda r plus 1 and subtract from 2. So what will I get? All I have that in 2, I have each term being multiplied with a different number, lambda 1, lambda 2, lambda r. But in the 1, every term will be multiplied by lambda r plus 1. So I will have d1 lambda 1 minus lambda r plus 1 plus d2 lambda 2 minus lambda r plus 1, so on until I have dr lambda r minus lambda r plus 1 xr plus dr plus 1 lambda r plus 1 minus lambda r plus 1. So this becomes 0, this term. Now I am left with these guys. They are distinct. So this is non-zero. This is non-zero. And I had just figured out that not all di are 0. But what does this equation then say? It says that I have come up with some constant. Let's call them d tilde. And d tilde I is just defined to be di lambda I minus lambda I plus 1. So I have come up with these new constants so that the linear combination is 0. And not all of them are 0. So this implies that xi are linearly dependent. But our assumption was this was the set which we selected to be linearly independent. So this is not true. So what could go wrong? So what went wrong was that I assumed that this r is less than k, so that I could put this extra vector, which screwed up things. So there's no such extra vector, and r is equal to k. So this implies that all of these guys, xi with distinct eigenvalues, are the maximal linearly independent vectors, the maximal set. So that means all vectors with distinct eigenvalues are linearly independent. So how does this help in proving our result? So our main goal is, so this is actually a nice thing to know, that if you have got two eigenvectors which have different eigenvalues, then you know that these two guys must be linearly independent. One cannot be constructed from the other. If you have three with three different eigenvalues, then they must be linearly independent. But if they happen to have same eigenvalues, then you are not sure. They can be linearly independent or they can be linearly dependent. And many a times what you end up with is that you have to select a set of linearly independent vectors over there in that space. So, but how does it help us in proving this theorem? So what is the theorem which I want to prove? At the start of the lecture, what I explained, that what is a diagonalizable matrix. So the theorem is about that this diagonalization exists. And it exists in a particular case. An n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. We know that if you have an n by n matrix, it has to have n eigenvalues. Some of them may be repeated, but there will be n eigenvectors corresponding to those eigenvalues. If those n eigenvectors are linearly independent, then A will be diagonalizable. And actually, it happens most of the time. There are very few matrices which are sick in the sense that their eigenvectors are not linearly independent, but most of the time they are, and if they are, then they are diagonalizable. So let's see how does this thing works. So first suppose, because we have to suppose both ways. Suppose that A has n linearly independent eigenvectors which are corresponding to eigenvectors x1, x2 up to xn with eigenvalues lambda 1, lambda 2, lambda n. I'm not assuming that these eigenvalues have to be distinct. Some of these eigenvalues may even be repeated. There's no such assumption goes into the theorem. The theorem only says that the eigenvectors should be linearly independent. Eigenvalues even can be repeated. Some of these eigenvalues can be repeated or they are same. So then construct an n by n matrix X by choosing the n columns of this matrix to be the n linearly independent eigenvectors of A. So you just construct it by hand, and what are you doing? You have these vectors available. You put them here. Now you have constructed this as an n by n matrix because each one of these x1, x2, x3 is an n column vector, and you have n of them, so you have an n column matrix. Now if I do this, multiply this multiplication by the rules of matrix multiplication is equal to this. That I multiply, we have done it many times, that I multiply A with the first column vector, that will give me a column vector back. Then multiply A with the second column vector, that gives me a column vector back. And this would be the result of this matrix multiplication. But these are eigenvectors. So they give me back these eigenvalues. And this I can write as this matrix multiplied by this diagonal matrix. Because remember, when I multiply this row with a matrix, how I can think of it as making the linear combinations with this. Lambda 1 times the first row, lambda 1 times the row, then lambda 2 times this row, lambda 3 times this row. So I get this back. You can just do this matrix multiplication, you get this back. So this is your matrix X, and this is a diagonal matrix with entries equal to the eigenvalues of A. So I've got this X AX is equal to XD with D diagonal, but X is invertible because its columns are linearly independent. So we did this theorem that if the columns of a matrix or its rows are linearly independent, then the matrix is invertible. Actually, it's invertible if and only if its columns are linearly independent. So it's invertible, that means I can multiply with X inverse. So that means A is indeed like this with D diagonal and having eigenvalues on the diagonal, eigenvalues of A on the diagonal. And actually, I even know that what is X? X is a matrix composed of columns which are eigenvectors of A. So if I have to do the diagonal decomposition of A, I have to find the eigenvectors of A and the eigenvalues. And I know that I can construct X by arranging the eigenvectors and putting in the middle the diagonal matrix with the eigenvalues. But one should note that X is not unique, because I didn't assume any ordering. Ordering doesn't matter. I could have put x3 here, x2 here, xn here, xn minus 1 later. It's still a matrix which is invertible, and it's still, when I'll act by A from the left, it will still produce the eigenvalues. The only thing is that in the diagonal matrix, my eigenvalues will be correspondingly differently arranged. So there are many different decompositions depending on how you arrange the eigenvalues, how you put the eigenvectors over here. And actually, we know that the eigenvectors themselves are not unique. We can multiply them with some constant, and that's fine. So you can multiply each one of these column by a different constant, and this x will still work. Well, we can also prove the converse of it. So suppose A is diagonalizable, then there exists a non-singular, that's what it means, x such that A is xd x inverse. That means I can write it like this by multiplying with x from the left. But I can write this A in terms of its columns. And so over here also I write it in terms of its columns. And this is diagonal. So let's call these diagonal entries to be D11, D12, D22, DNN. And I know how does a diagonal matrix multiplies to this. So this just gives me and on this side, I know that this multiplies in this way. Now, since these two matrices are equal, implies the columns are same. So that means for each of the column of x, I get this equation. This implies xi are eigenvectors of A and dii are the corresponding eigenvalues. So I have found that if it's diagonalizable, then I have these these vectors are its eigenvectors. But since x is invertible, so these xi are linearly independent. So I found that if the matrix is diagonalizable, then its eigenvectors must be linearly independent. And the other way around also works. So let's do some examples. Let's consider this matrix. So if I find the eigenvalues, so it's determinant of this guy plus 6 is equal to 0. So I have minus 10 plus 5 lambda minus 2 lambda, then plus lambda square plus 6 is 0. So lambda square plus 3 lambda minus 4 is equal to 0. So this is equal to I'm using minus b plus minus b square minus 4ac over 2, the quadratic formula. B is 9 minus 9 plus 4, A is 1, C is 4 over 2. So I get minus 3 plus 1 over 2 and minus 3 minus 1 over 2. So I get minus 3 plus 1 minus 1, and lambda 2 is minus 3 minus 1 minus 2. Let's see if everything is correct. Minus into 2 minus lambda, 2 minus lambda minus outside 5 plus lambda and minus plus 6. So 5 into 2 minus 10, 5 into lambda plus lambda minus 2 lambda plus lambda square plus 6 is equal to 0. And so I have lambda square plus 3 lambda minus 4 is equal to 0. So this looks fine. Now let's find the eigenvectors. So the eigenvectors are these are the eigenvectors I'm trying to find. So you're trying to solve this. So finding the solutions of it. So A is 2, and I'm putting my eigenvalues minus 1 and minus 2. So 2 minus 1. So I get a 3 minus 3, 2 minus 5 and minus 1 1 lambda was -1. So -5 and +1 gives me -4. So 1 minus 1 dividing by 3, then -2 times, add it over here, 0, -2 plus 2, -2 plus 2, this gives me -2, then this goes to 0, wait, I think there was a mistake in finding the eigenvalues, because see, this is giving us something inconsistent.
सर
जी
सर क्वाड्रेटिक फार्मूला में 1 आ रहा है आपके पास एंड इट देयर शुड बी 5 हियर -3 +5 एंड -3 -5
कहाँ पे?
सर क्वाड्रेटिक फार्मूला में
Uh,
9 + 16 and under root 25 will be
oh, yeah, I don't know. I assumed a minus in between. So that was the mistake. 9 plus 16, which gives me 25. So I get a 5 here, right? Is this okay, right? So my one eigenvalue is +1, and the other eigenvalue is -3, -5, so -4. Thank you very much. So now when I do this, I'm first doing it for the eigenvalue +1. So then I get 2 minus 1, my matrix becomes 2 minus 1. So I get let me erase all of this. So 2 minus 1 gives me a 1 here. And then this is just -3, 2. And then I have -5, -1, which gives me a -6. Now, if I want to bring this to the echelon form, then I multiply this by -2 and add over here. So I get a 0, a 0, 0. So that means if I write this as like this, x2 is free and x1 is 3 alpha. So my matrix, I can choose alpha anything, I can choose it 1. So I can choose, this would be the eigenvector, one possible eigenvector. And the other eigenvector is 2 minus -4. So 2 plus 4, 6. This is for lambda is equal to -4. And 3 and -3 and 2 are just over there. And over here, I had a -5 and minus of -4. So this -5 plus 4 is a -1. So I can first divide by a 3. minus 1 times added here, 0, 0, 0. I don't even have to make this 1. I can just use my logic that x2 is free and 2 times x1 minus x2 is 0. So x2 times x1 is x2. So if I choose x2 to be 2, then x1 would be 1. So I can take this vector 1, 2. So one is 1, 2, and the other was 3, 1. These are the two eigenvectors. And I am hoping that when I construct this x, then I construct its inverse. So 2 times of the first row added below, minus 2 plus 2, 0, minus 6 plus 1, minus 5, minus 2 plus 0, minus 2. And now I have 1, 3, 1, 0, 0, minus 5, minus 2 over 5, 1 over 5, sorry. I can multiply by minus 1 over 5. And then minus 1, minus 3 times this added above. 1 minus 3 times this 0. So minus 6 over 5 plus 1. That gives me minus 6 plus 5 minus 1 over 5. And minus 3 plus 3 over 5. Or is it minus 3 over 5? I'm multiplying it with a minus 3. Mm, uh, plus 3 over 5. So that means x inverse is 1 over 5 minus 1, 3, 2, minus 1. Three, 1, 1, 2. Okay. So that's the x inverse. Now our expectation is that when I'll do this, and what is A? A is 2 minus 3, 2 minus 5. and x was 1, 2, 3, 1. This should give me a diagonal matrix. So I get 2 plus 2, 4, minus 9, no, sorry, 2 plus 2, 4, 6 minus 3, 3, 2 plus 2, 4, 6 minus 5, 1. And now minus 4, minus 4 plus 12 gives me 8. This is not, there's some mistake. Minus 3 plus 3, it is coming out to be diagonal, but minus 3 plus 3, 0. 2 times 4 minus, yeah, there's some mistake over here. Anyway, we can't really go back and figure out. I should have done this whole thing in advance. But let me just write what should happen. This is A. 2 minus 3, 2 minus 5. This should be equal to the x inverse here and the eigenvalues, which are 1, minus 4, 0, 0, and x coming over here, which is, it could be just that we did it in the opposite order. X was 1, 2, 3, 1. Let me try this. Let's put, because see, we get it this way. Ax is xd, so I should be having A is equal to xd x inverse. Let's try this. This was my defining equation. Ax was xd. This is what I had got. So A is xd x inverse. So if I check this, and D should be x inverse. Yeah, I was right. Hmm.
सर मैट्रिक्स मल्टीप्लिकेशन में तो मिस्टेक नहीं है।
एक सेकंड ठहरें। हाँ, वही मैं कह रहा हूँ ना कि कहीं वहाँ पे मिस्टेक हुई है, but I'm not going to go back and fix it. It's gonna take too much, too long.
नहीं सर, जो अभी अभी ऊपर जो आपने किया एक्स इनवर्स ए एक्स वाली, जी सर।
क्या मिस्टेक है?
सर ये जो आपने ए और एक्स को मल्टीप्लाई करवाया,
हाँ, इसमें क्या है? 2 plus 2, 4.
सर
Then
माइनस फोर आएगा ना।
नहीं, पहली एंट्री में क्या आएगा? 2 plus 2, 4. Then 6 minus 3, 3. Then 2 plus 2, 4. then 6 minus 5 1. ये तो ठीक है. Oh, immediately I have a trouble. So I think there is some mistake in
Sir,
compute.
it's the
Hmm? बोले बोले.
-4, 3, -8 and 1.
ये
सर ये
कैसे
4
है?
और 4 कीजिए. सर 2 1s are 2 and -3 multiplied by 2 6 and 2 minus 6 4 होगा. फर्स्ट रो और फर्स्ट
Oh
कॉलम को
yeah,
मल्टीप्लाई किया.
yeah. So 2 minus 6 minus 4.
-4 and -8 आएगा, बाकी दोनों ठीक.
6 2 is okay. 6 minus 3 3,
यस.
then 2 and minus 10. So it gives me, ये -4 है
माइनस.
और ये है
यस.
-8
8. तो ये
और
1 ही होगा.
1 ठीक है.
जी.
ठीक है. So now see what happens. So now I have 4 and minus 24. So 20, right? No, 4 and minus 24. So minus 20. Then minus 3 plus 3 is 0. Then minus 8 plus 8 0. Then 3 times 2 6 and minus 1 5. So it gives me what I wanted. Yeah, so we have confirmed it. Thank you very much. That when I do this, I do diagonalize it. And on the diagonal, I'm getting the eigenvalues. Let's quickly check the other facts. The determinant of A, I don't even have to go to the diagonal. Because of this construction, I know that these things work. That if I directly compute the determinant of A is 2 minus 3, 2 minus 5. Lecture 21. Yeah. So determinant of A is minus 10 plus 6 is 4. But my claim was determinant of A is the product of eigenvalues. So eigenvalues are, well, this is minus 4. Eigenvalues are minus 4 times 1. So it is minus 4. And trace of A, which is the sum of the diagonal entries, is minus 3. But this is also equal to the sum of the eigenvalues. So let's stop here. When is the homework due? Do you remember? Homework 4?
फ्राइडे सर
So
11:30
I
PM.
definitely will extend the deadline because I don't think people have caught up. So Friday means tomorrow, right?
Yes.
So I'm gonna extend the deadline, and I'll appreciate if because it may take me some time to announce it. If you could, someone could post it in the group. I'll extend it, and I'll also similarly I'll try to post a few. I know I have been lagging behind a little bit because I know that people are way back on the 14th lecture so far when I look at the YouTube. So I'll post about 2 3 more tutorials, and I'll post one more homework, but I'll keep the deadlines very flexible so that people can catch up and do all the work. Okay, so let's stop here.